Here's a question for you. Can you tell me what the number 3 actually is? Seriously. You all know what it means to have 3 of something, or for something to be third in a list, but what is 3? If I asked you to define the colour red, for example, you might point out some red things. These things over here are red, these things are not red, and this one, maybe. But what is red itself? When you point out some red things, you're describing objects which have the redness property. It's the descriptive version of red, the adjective red. These things have it, these things don't. But what is red itself? What is the noun red? Well, we can define red scientifically. Visible light falling in a certain range of wavelengths is red. Now, this definition has some fuzzy edges, where does red stop and orange begin? But it's a fairly concrete definition. And the other thing I like about it is, like me, it doesn't really care how you feel about it. Is this thing red? Well, does the light it reflects fall in that range of wavelengths? If yes, then red. And that's really important. Definitions shouldn't depend on how we feel in our gut. They should be robust. So can we do the same for the numbers? Can we do the same for 3? This collection has the 3ness property. This one does not. It's the descriptive version of 3, the adjective 3. But what is the noun 3? Do we have a scientific definition for 3 that doesn't care how you feel about it? Coming up with a definition for the noun 3 is harder than you might think, but mathematicians have a way. I'm going to share that with you today, but just brace yourself, alright? This is going to be a long and strange journey. We're going to meander through several topics, including what we know about physical units and paradoxes. At some stage, we'll confront the brick wall of human intuition. We'll even be forced to abandon all knowledge that anything exists at all. But the reward will be something logically pure, providing a solid bedrock of mathematical understanding. There will also be cake. I'll explain later. First, let's address that question that you might have on your mind right now. It's the same question that we mathematicians are always burdened with. Why? What's the point? Why do I need to know this? And I know what your maths teacher might have told you. You never know when you might need this in the real world. Well, spoiler alert for life, you're not going to need 90% of the maths you learn in school ever again. Some of it you will need, like the other 20%, but let me convince you why we should demand a concrete definition of numbers. When you really think about it, a lot of our calculations boil down to just one thing: counting. When we do a multiplication like this, for example, we're really just doing a big addition. And when we do a big addition, we're really just counting things. How many do I have in total if I have 7 and then another 7 and then another 7 and so on? How many do I have in total? I'm just counting. And in order to count, we should know what the numbers are. Surely. How do we know that we always get the same answer, that our numbers are always the same? How do we know that there isn't some absolutely horrible, nightmarish calculation we can do that will produce conflicting answers, whether we do it by machine or using a different method? Would you bet your life on the fact that this will give the same answer regardless of who does it, what method they use, whether they use a computer? I know I would, but that's because I live life on the edge. But would you? Now, this will always give the same answer, but in order to prove that, we need to know what the numbers are. We need a definition that we can all agree on so that our calculations are consistent, and in order for it to be rigorous, it should be a definition that doesn't care how we feel about it. A lot like the definition of red. Let me give you a more practical example so you can visualize what I mean. This bag of sugar is 1 kilogram. It's what some of us grew up using as our benchmark for what 1 kilogram is. How much does this weigh? About 3 bags of sugar, about 3 kilograms. Now, if you're more of a pounds and ounces sort of person, don't worry about it. Just go to your keyboard, press Ctrl W, and it will close the video. Now, while this is a good benchmark for us, it isn't a good benchmark for scientists. Not every bag of sugar weighs the same. So what benchmark should scientists use so that they always know exactly what 1 kilogram is? Well, back in the olden days, and I'm talking way back, pre-2019, if you can imagine such a time, there used to be a platinum iridium block sealed in a laboratory in Paris. known as the International Prototype Kilogram, or IPK, the mass of this block, whatever it was defined to be 1 kilogram. It was also affectionately referred to as la grande ca, or as we from up north call it, la grande ca, because people from the north can learn French as well. If I want to know whether this bag of sugar really is 1 kilogram, I can check it against the IPK. Now for most people, it doesn't matter if this bag of sugar is 1 kilogram or a few grams either way, but if I performed a science experiment with the sugar and required all other scientists to perform the exact same experiment, they would have to use exactly the same amount of sugar, i.e. 1 kilogram. So blocks were made, checked against the IPK, and sent to scientists everywhere so that all scientists had the same 1 kilogram mass to work with. They would all agree on the definition of a kilogram. There is sugar everywhere. Definitely not 1 kilogram left in there. We did the same thing with the meter. The meter that we use today was originally defined as follows. You take a straight line from the North Pole through Paris and keep going until you hit the equator. Divide that line up into 10 million tiny little pieces, and each of those little pieces is defined to be 1 meter. And bars, each 1 meter long, were produced all the same length and sent to scientists everywhere so that all scientists had the same 1 meter length to work with. And I don't know why the French kept getting involved in trying to sort this out. As a British person, it makes me grateful that someone did. Same for temperature. The temperature water freezes at is called 0, the temperature it boils at is called 100. Split that up into 100 pieces, and each piece is defined to be 1 Celsius. And if you're more of a Fahrenheit person, so you get the idea. Regardless of how you feel, the IPK has a certain mass, and we define that mass to be 1 kilogram. Regardless of how you feel, there exists a temperature at which water freezes. So we call that 0. Robust, concrete definitions. In fact, it's not just units for temperature, mass, and length that we can define in this way. We can come up with concrete definitions for these 7 base units, and all other physical units can be written in terms of these, like the joule, the newton, the Weber, the sievert. They can all be defined using just these 7 base units. For example, 1 newton. It can be defined as 1 kilogram meter per second squared. Every unit can be broken into the 7 base units, and there are concrete definitions for those units. In chemistry, every molecule or interaction can be broken into the constituent elements, and some rules for how they relate. What is the definition of an atom with 19 protons? It's defined to be potassium. There are rigorous, concrete definitions for each, and it doesn't matter how you feel about it. In mathematics, every proof involving numbers or calculation can be broken down into the numbers themselves. We should have rigorous definitions that don't depend on our gut feelings. Chalk everywhere. So enough justification, let's give it a go. You've had some time to think while I've been prattling on about French ingenuity. Let's try to define what the numbers are. Let's start with 3. Let's try and define the number 3. I'm going to try and define it how I think many of you think we ought to define it, and that is to say that 3 is what you get when you have 1 more than 2. Now that's fine, but we've kind of pushed the problem back a step. Now we're stuck trying to define what the number 2 is. Okay, well, it's surely just 1 more than 1. And here we hit a bit of a problem. We can't really say 1 is 1 more than 0, because then I'm using the word 1 as part of the definition of 1. I need another way of defining 1, and here's an approach many of you might take. We could say that 1 is the smallest whole number amount we can have of something. Like this is 1 cake, but this is not 1 cake. Yet I do refer to it as 1 slice. And we need to be careful here. I am using the descriptive version of 1 again, the adjective 1. This thing has the oneness property, but I want the noun 1. What is 1 itself? Now, you might say I'm being awkward and pedantic here, and you're absolutely right, I am, but there's a reason for it. It's because I want the definition of numbers to be so rigorous and concrete that no one can argue with it. It's just a frustrating definition because it's a slippery one. You try to grasp hold of it, but it gets away from you. And why is it frustrating? I think it's because of intuition. Now, intuition is great. It's like cake. We all love it. We all trust it. But deep down, we know that in and of itself, it probably isn't enough. Intuition is like another sense. It gives us a gut feeling for how to solve problems. We all know intuitively what the number 3 is, and we find it really hard to overcome that gut instinct to figure out a concrete definition. But I want to, because our intuition can lead us astray. Let me show you how. Take, for example, a collection of all the integers. Positive, negative, 0, all the whole numbers, they're all in there. And it goes on forever in all directions. You're just going to have to use your imagination because despite Amazon's efforts, I still only have a finite amount of cardboard. Now, let's take a collection of all the even integers. So 0, 2, 4, 6, etc., minus 2, minus 4, minus 6, etc. Again, going on forever in both directions. And here is my question. Which collection is bigger? Well, surely this one is bigger since it contains everything that this one contains and more. If anything, it should be about twice the size. So intuitively, this one is the bigger collection. But thinking about it another way, if we pair these up, and I've just tipped those out in the least helpful way possible, but thinking about it another way, if I pair all the numbers up in this collection with their doubles in this collection, then every member of this collection is paired with a member of this collection. So all the members line up perfectly 1 to 1, and so both collections must have the same size. So our intuition first told us that one must be bigger than the other, and then our intuition tells us that they both have the same size. So which is it? This is known as the Galilean paradox, and Galileo once wrote a letter about this, saying that his intuition is guiding him to two conflicting answers, and they can't both be correct. It's a lesson that trusting intuition alone is not enough. Because there is an answer to this question. It is true that either they're both the same size or one is bigger than the other. There is an answer, but we need specifics. We can't rely on intuition alone. We need concrete definitions. What do I mean by bigger? What do I even mean by a collection? Let me give you the gist of how this is going to work. What we want is like an international standard 3, like we did with the kilogram, but with the numbers. Let's say, for example, that this box of 3 cakes is literally the number 3. So, like we defined the mass of the IPK to literally be 1 kilogram, we could say, if anyone ever asked you what the number 3 was, you say this box of 3 cakes is literally the number 3. How would that help us? Well, we could have such boxes for all the numbers. So now we have rigorously defined all the positive integers. So this is literally the number 4, for example. And the magic thing about this is that this actually allows us to count. Remember, that's what we really want the numbers to be able to do, right? We want to be able to count things. Let me show you how. So I have a collection of pencils here. How many pencils do I have? Well, I can look at my international standard numbers and I can see that from 2 downwards I have more pencils than cakes, and from 4 upwards I have more cakes than pencils. Only with this specific box here do I have the exact same number of cakes as pencils. And how do I know that? Well, what I can do is I can play a game of matchup and I can match the cakes with the pencils exactly 1 to 1 and see that my collection of pencils is the exact same size as the collection of cakes. And since this collection of cakes is called the number 3, I know that I have 3 pencils. There's cake everywhere. And if you think I'm not going to eat these just because I've impaled them with a pencil, you are sorely mistaken. Now, there is a slight issue here. One of those rare times the wisdom of a mathematician coincides with that of a dietitian. Cake just isn't good enough. We could use this definition of 3. We could even go as far as to lock these cakes up in Paris and say that whenever we wanted to count something, we would refer to le grand gâteau. But we know there are an infinite amount of numbers, so we would require an infinite amount of cakes. And that sounds fantastic until you realize, where are you going to put them? After all the hard work the French have done sorting out our metric system, do you really think it's fair to burden them with such a horrendous storage problem? We don't want our international standard numbers to contain anything physical. We want them to be abstract, existing in mind alone. But what can we put inside an abstract box? 3 abstract thought cakes? Now there is an elegant answer to this, but we must tread carefully. We're about to start making some abstract boxes, or as we mathematicians call them, sets. You see, mathematicians were happy to create sets for centuries without worrying too much about the concrete definitions of numbers and sets and everything like that. Guided only by their unconstrained intuition, it almost led to disaster. Let me show you how. Now brace yourself for some braces, or as we Brits call them, curly brackets. Or if you're from up north like I am, you call them curly brackets. Now, we just use these curly brackets to denote a set, a collection of objects. And inside the curly brackets, we have the elements of the set, the members of the set, the things that are inside the set. So, for example, this is the set containing the numbers 1, 2, and 3. Now, I know that I haven't actually defined what the numbers 1, 2, and 3 are yet. That's the whole purpose of the video, after all. But just bear with me, alright? Because I just want you to get used to what the idea of a set actually is, and then we're going to use them later. Now, if I have a very large set, it becomes very cumbersome to actually list the elements out. Even worse if you've got an infinite set. So instead of actually listing all of the elements, what we can do is we can write some instructions for what belongs in the set and what doesn't. So I could have this set, the set of all integers n, such that n is even. So I have the universe from which I'm pulling the elements, in this case the integers, and then a statement. And when that statement is true, that element belongs in the set. So for example, I take an integer like 1 and I make the statement 1 is even. That is a false statement, so 1 does not belong in the set. Whereas a number like 4, I make the statement 4 is even, and since 4 is even, it does belong in the set. So this is the set of all even integers. Now let's make things just a little bit more complicated. So when you think about it, I don't just have to have sets of numbers. I can create sets that contain anything. Earlier I had sets of cakes, but we can also have sets of sets. So get your head around this one. Here I have the set of all sets x, such that x contains 3 elements. Let's just unpack what this actually says. So I'm pulling from the universe of sets, like before I pulled from the universe of integers. So I'm building a set of sets. And here my statement about what belongs in this whole set is that the size of the set has to equal 3. These vertical bars on either side of x there, that just means the size of the set. So, for example, if I put vertical bars around this one, I would get infinite, because it's an infinite set. If I put bars around this one, I would get 3, because it is a set containing 3 elements. Now this one, this is the set of all sets which contain 3 elements. So that set of 3 cakes I had before, that goes in there. This set that contains 3 elements, that goes in there. Okay? Now contrast it with this one. Now this one is the set of all sets. It's upside down. That's not the point of contrast I was hoping for. This is the set of all sets x, such that x contains at least 3 elements. So it's all the sets that contain 3 elements, all the sets that contain 4 elements, all the sets that contain 5, and so on. So this guy belongs in there, because it does contain 3 elements. Also, this guy appears in here, because it does contain at least 3 elements. It's got an infinite number of sets. And this guy also appears in this one, because this guy contains at least 3 elements. Now, here is the really confusing part, alright? Just bear with me. This set we've just seen contains at least 3 elements. So it actually contains itself. You will find this set inside this set because it fits the rule of containing at least 3 elements. So this set does not contain itself because this set definitely has more than 3 elements. This is an infinite set. It is not a set that contains 3 elements, so it doesn't belong in there. This set does contain at least 3 elements, so it does belong in there. So we have some sets that don't contain themselves, and some sets that do contain themselves. Okay, now, are you ready for this? Because this is a huge problem that Bertrand Russell discovered all the way back in the early 20th century, and that is when he discovered this set. This is the set of all sets X, such that X does not contain itself. So this seems fair enough. This is a set that does not contain itself, so we put it in there. And we said before that this set does not contain itself, so we put it in there. But we agreed that this set does contain itself, so it doesn't go in there. So, some sets don't contain themselves, in which case we put them in, and some sets do contain themselves, in which case we don't put them in. And that's all well and good, but here is the problem. Does this set contain itself? Let me say that again. Does this set contain itself? Well, if it does, then we actually shouldn't put it in there, because we only want to put in the sets that don't contain themselves. But if it doesn't contain itself, it belongs in there. And if it's in there, then it does contain itself, so we should keep it out. But since it doesn't contain itself, now we need to put it in, because it does not contain itself. It's a paradoxical set. We cannot decide whether this set contains itself. It's a lot like the liar's paradox. You know, this statement is false. Well, if it's true, then it must be false, because it's saying that this statement is false. But if it's false, then this statement is false, which means the statement is true. But if it's true, it's false, and so on. Or another example is the barber's paradox. You know, I will shave any man's face who does not shave his own face. So I only shave men who don't shave themselves. Now, does that barber shave himself? Well, if he doesn't shave himself, then he does shave himself. But then he does shave himself, which means he doesn't shave himself. And you see the problem. So long story short, this is a paradoxical set. Why is that a problem? Well, remember, we want to use sets to define things as simple as the numbers. And if we've seen that paradoxes can arise in sets, then it's not a good idea to use something paradoxical to then define something as basic as numbers. Why did this paradox arise? Where did we go wrong? Well, once again, we appealed to one too many delicious slices of intuition. We considered ourselves set theoretic gods, able to create whatever set we fancied without actually worrying about the hard definitions. What is a set? What is a number? And as a result, we ended up with a paradoxical set. So what do? What we must do is start from scratch, making the fewest possible assumptions about what we can and can't create. Every theory, every body of knowledge requires some foundational assumptions. You've just got to make sure that those assumptions are limited and as reasonable as possible. So let's start from the basics. And when I say start from scratch, I really mean it. I want you to pretend that we know utterly nothing about mathematics. Let's get rid of all of it. Sets, cakes, let's get rid of our fickle intuition, let's get rid of all of it. I would say that we're going to start from the ground up, but we're not even going to assume that the ground exists. What then? If something exists, and that's a big if. I'm going to put this here to remind ourselves that we don't know whether these things exist. This is all in hypothetical if space. If something exists, let me show you what I can do. I'm going to use these to represent my hypothetical nebulous somethings, alright? So let's say that these things exist in our hypothetical if space. I can still feel somewhat justified in putting some of these into figurative collections. So let me show you what I mean. Let's say I pick some of these nebulous somethings and I put them into a collection like this, okay? So I've kind of partitioned my nebulous if space into an in-group and an out-group. So I've not created anything new here. All I've done is I've said, okay, these nebulous somethings are in the group and everything else is outside of the group. I could even create a different group if I like, maybe these guys over here that are inside a different group and everything else is outside the group. I can even create this one. So take a look at this. This is the collection with the unique property that nothing is inside and everything is outside. What am I doing here? Well, what I'm doing is I'm saying that regardless of what actually exists, we can still feel somewhat justified in creating these collections. In fact, let's just assume, if you're still uncomfortable with it, you're going to have to take the leap at some point. Assume that we are allowed to create these collections with whatever exists. But let's temper that assumption a little bit. Let's make sure that these collections are really, really rigorously defined. So let's create some rules that we will stick to so that our collections don't go too crazy like they did with Russell's paradox. And there's going to be 5 of these rules. Now there's no way around this. All the rules are very simple, but we do need to just define what those rules are in order to proceed. So let's go through each one in turn. The first rule is called pairing. Pairing says that if 2 things exist, then I can create the set containing those 2 things. The second rule is called union, and it states that if 2 sets exist, then I can create the union of those 2 sets. And the union is just the set that contains everything that the first 2 sets contained. The third rule is the subsets rule. The subsets rule says I can take a subset of a set that already exists. So if I have a set that exists, I can extract some of them to form a new set. The fourth rule is called extensionality. Now this is just a fancy way of saying that a set is defined only by its elements. These sets are considered to be the same because they contain the exact same things. So this is when sets are equal to each other. Now there's a subtle addition to that rule, an extensionality extension if you will, and that is that we don't really care about duplicates when building sets. These 2 sets are considered to be the same set. And why is that? Well, if I ask you, is the red thing in here? You would say yes. Is the red thing in here? Yes. For anything else, is it in here? No. Is it in here? No. So these sets really are the same. I like to think of this as we can simplify this set into this set. Since they're both the same, we'll stick with the simpler version. So this is the proper way of writing this set. Now the last one is called regularity, a little bit different from the others, and I'll explain more about it at the end of the video, but for now, all it means is we're restricting ourselves so that we're not allowed to create sets that contain themselves. If a set happens to contain itself, we don't consider it to be a proper set. So we're just limiting ourselves in that way. It does have a more technical definition, but for now, just bear with me, alright? Because I don't want to get too technical at this stage. If you're interested, I will explain it at the end. So there we have our 5 rules. And the astounding thing is that with just those 5 rules, we can actually go ahead and define the numbers. But before we get there, I want to do one of my favorite things that you can do in mathematics, and that's to derive something new from that which already exists. I'm going to make a 6th rule. Unlike the other rules, it's not going to be a foundational assumption. I'm going to prove that we can do something new based on the first 5 rules. My rule is this. Given a thing that exists, I can create the set containing that one thing. And why am I allowed to do this? Well, remember, if I have a thing, let's take a duplicate of that thing, and using the pairing rule, I'm allowed, if 2 things exist, to put them into a set. But by extensionality, I don't care about duplicates. This set is considered the same as this set. So I started with this, and I finished with this. So it's a bit of a shortcut. So instead of going through the pairing and extensionality steps every time, I can just say, whenever I have one thing, I can, through a series of those 5 rules, end up with this. I'm going to call it the singleton rule, since we refer to sets that contain just one thing as singleton sets. So remember, that isn't a foundational assumption. I've assumed that we can use those 5 rules however we like. but a consequence of those rules is that we have a sixth rule. Now I know what you're thinking, this is all well and good, big deal, you've got your 6 rules, but you can only use them if things actually exist, and I'm still stuck in this hypothetical if space, where I don't actually know whether anything actually exists. Remember when I said the pairing rule, if 2 things exist, I can put those things into a set. If those 2 things exist, but I don't actually know whether those 2 things exist. Except, we're going to take a bit of a leap here. Remember when I defined this guy that had the unique property that everything is outside and nothing is inside? We're going to take the leap and say that this thing actually exists. And how can I justify that? Well, if you're like me, and you're like most people, and you're like Descartes, you know that at least something exists. At least something. Anything. At least something does exist. And by the singleton rule, I can put that into a set. And now, I'm going to use my subsets rule. And I'm going to say, I can choose some elements from here and place them into here. So I'm going to choose to select none of them and put them in here, thereby creating a new set. And this is the set that has the unique property that nothing is inside and everything is outside. In any case, I hope you'll take the leap with me and agree that this thing exists. It's so important that it even has its own name. We call it the empty set. Or if you're from up north like I am, we call it our kid. And this is where the magic happens, because we can apply all of the rules we've already defined with this set. In fact, get out of here, because we know for certain that this thing exists. We don't need if or hypotheticals, we know this exists. It might be the only thing we know exists, but that's all we need. For example, let's use the singleton rule. I can take something that exists and put it into a set, and thereby create a new entity, the set containing the empty set. Now you might wonder, have I actually created anything new? Are these sets actually distinct? After all, there's nothing really in either of them. But remember, by extensionality, a set is defined only by its elements. This set here contains one thing, the empty set. This set here contains nothing. So a box containing a box is different from a box containing nothing. So these are necessarily distinct. I could do it again if I like. Let's use the singleton rule again and put this into a set all by itself, thereby creating the set containing the empty set. And what I could do is use the singleton rule again and again and again and create an infinite number of sets, like a whole set containing the set containing the set containing the set containing, and so on, like a Russian doll with the empty set in the center. In fact, I encourage you to pause the video here and see what sets you can create. It's amazing what you can create with just those 6 rules. But let's remember why we're here. We're here to define the numbers, and we are finally ready to do so. I'm going to make up a new word now, as mathematicians love to do. The word is successor. And what a successor is just an application of some of those rules to get from one set to create another. So we're going to start with this one, and we're going to make its successor. Now, to create a successor, what we do is we duplicate the set. We put the duplicate into its own box. I can do that using the singleton rule. And then I union everything together. So to union everything, I take all the contents of this set and all the contents of this set, and thereby create a new set. So this set is the successor of this one. Why do I need to do that? Well, something very, very special is about to happen. Let's take the successor of this one. So I take a duplicate, I put it into a set all by itself, and then I union the results together. So take all the contents of this one, and I take all the contents of this one, and thereby create a new set. One more time, let's take the successor of this one. So we take a duplicate, we put the duplicate into a set all by itself using the singleton rule, and then we union everything together. So I take all the contents of the sets here all together into one set. So the successor of this one is this set here, and so on. We could keep going, but let's just stop here for now. Now I'm going to indulge in the creation of more definitions here. Again, not creating anything out of thin air when I do this. I'm just using language to assign words to things that are important. You might have heard the word that I'm about to define before, but I don't really care. My definition will be very specific. Now the word is 0. I'm going to assign the word 0 to this set here. So one name for this set is the empty set, another name for this set is 0. I'm going to define another word now, and the word is 1. I'm going to assign it to the successor of 0, which was this set here. The successor of 1 I will call 2, and the successor of 2 I will call 3. The successor of 3 I would call 4, and so on, and there we have it. Using nothing more than our own reason and agreeing that we can put things into figurative boxes using some basic foundational rules, we've created the international standard numbers. We don't even need to lock this away in Paris. We can store it in our own minds because it's purely abstract. Instead of containing 3 cakes, it contains 3 sets. How many pencils do I have here encrusted with cake? Well, from here and down, I have too many pencils than sets. From 4 and upwards, I would have more sets than pencils, but here, exactly here, I've got the exact same number of sets inside this international standard 3 box as I have pencils, and therefore the number of pencils perfectly coincides with the international standard 3, so I say that I have 3 pencils. These are exactly like international standard numbers that guarantee that at the foundation of mathematics we have something strong and secure on which to build our knowledge. So good! What's more is that we can actually go from here and use these international standard numbers to then define how to add numbers, how to multiply numbers, or how to define the negative, the rational, the real, and even the complex numbers. Everything can be built from this foundation. Now, does this mean that mathematicians permanently think of numbers as these sets? No, not really. Maybe some of them do, but no. After assigning the labels 2 and 3 and so on, we can use the everyday language of numbers that we're used to. All this means that if we strip away all of the shorthand, we have robustly, rigorously defined numbers hiding underneath. I don't season my food with sodium chloride. I season it with salt. Salt is just a shorthand word, but what's hiding underneath is something that is well defined, which is sodium chloride. It's like how I don't say that I push on this table with a force of 100 kilogram meters per second squared. I just call it 100 newtons. Although, have you seen me? It's more like 2 newtons. But I can always unpick the Newton shorthand to get to the rigorously defined units hiding underneath. When I talk about the number 3, I don't always think about this set, but if I need to, I can unpick the word 3 to get to the rigorously defined concept hiding underneath. So, there we have it. The next time someone asks you to define the number 3, you say, it's simple. It's just the set containing the empty set, the set containing the empty set, and the set containing the empty set, and the set containing the empty set. And some people say maths is complicated, but you and I would both agree that it's a piece of cake. Thank you so much for watching. I really, really appreciate it. Just a couple of notes to end on. So I mentioned the rule about regularity. Now, what the rule of regularity actually states, the proper definition of it is that if you have a set that isn't the empty set, then it must contain an element that has no elements in common with itself. Let me see if I can break that down a little bit. So this is a set that contains 2 things, this set and this set. Now, the axiom of regularity says that in order for this to be a legitimate set, it must contain at least one element that has nothing in common with the original set. And we can see that this and this, they have nothing in common. This contains 2 things, the white box containing the green thing and the red box, whereas this only contains the green thing. They have nothing in common. It's a very awkward and sticky definition, and I didn't want to get into that during a video that's kind of aimed towards everybody. The main consequence of the of regularity is that it forbids the creation of sets that contain themselves. And that's the main point, because we're trying to avoid paradoxes like Russell's paradox, which, by the way, did cause, real issues in the foundation of mathematics. Set theory lies at the foundation of mathematics. As I said at the end of the video, once we have our international standard numbers, we can go ahead and define other types of number and go from there. And set theory really does underpin a lot of areas of mathematics. So that's why it's so important to get right. If you have a paradoxical foundation and you try and build on it, then whatever you build could be, dubious. It's like building on quicksand. So what we've actually done in this video is we've explored the Zermelo-Fraenkel axioms of set theory. What on earth does that mean? The axioms are the rules like pairing and subsets and union, etc. We call them axioms. They are anything that we presuppose to be true. So they are our initial assumptions, and then we build up our theory from the axioms. Like we did with the singleton rule, you can build that out of pairing and extensionality, and we define the numbers using only those rules and the fact that the empty set exists. So it's called Zermelo-Fraenkel set theory, or ZF for short. Sometimes you'll see it referred to as ZFC, but that's a different theory. That's all the axioms of ZF, plus one extra axiom called the axiom of choice, which is a little bit more of a contentious axiom, because while it's required to do a lot of mathematics, it also leads to the creation of some pretty weird things. So it's a bit of a contentious issue as to whether to include the axiom of choice or not. In ZF there are actually more axioms than what I went through. So there's the axiom of infinite sets, which says that an infinite set exists. It also has as one of its axioms that the empty set exists. So I went through a lot of trouble to convince you why we should feel justified in saying that this exists, and I kind of prefer to tell the story that way, because I like the idea of, the fewest possible number of assumptions is what gets you through. So if you can avoid one of the axioms that just says the empty set exists, then I think that makes for a better story. It's worth pointing out that ZF isn't the only axiomatic theory of mathematical foundations, but it is the most common one and the most popular one, at least from my experience. And, you don't need a lot of detail and to know all the ins and outs of it in order to get at a definition of the natural numbers, which is what this video is mainly supposed to be about. This is the first real video that I've made. It's taken me a really long time to make it the way that I wanted to make it, how I envisioned, years ago. So if you feel like supporting me, I would really, really appreciate it. You can do that by buying me a coffee using the link below. You can also check out the other videos on my channel, but it's pretty sparse at the moment. The only other thing that's on there is that earlier this year, I did a fundraiser. I did 24 maths exams in 24 hours to raise money for Refuge, a UK-based charity that helps women and children victims of domestic violence. So if you want to check that out, then please feel free. This has been another proof under another roof. Until next time, thanks for watching.